Welcome to Gradient Canvas. Today we're going to learn about the supervised learning problem and why we split our data into training, validation, and test sets. Here's a model that gets every single training example right. 100% accuracy, and it's completely useless. How? Because it didn't learn anything, it just memorized the answers. The real job of a machine learning model was never to ace the data we already have. It's to make good predictions on data it has never seen. That one shift, from fitting the past to predicting the future, is the whole reason we split our data into three piles: training, validation, and test. Let's see why. Let's ground it. In supervised learning, you're given examples, each with an input and a correct answer, a label. Say the size of a house and the price it sold for. Input, square footage. Label, price. From a pile of these labeled examples, the model's job is to learn a function, a rule that maps any input to a predicted output. Feed it a new house's size, and it should return a sensible price. That's it. Inputs, labels, and a function learned to connect them. Everything else in this video is about making that function good. So how does it learn the function? A model is really a family of functions with adjustable knobs, parameters. Learning means turning those knobs until the function's predictions are close to the labels. We measure close with a loss. For each example, how far off is the prediction from the truth? Add that up, and training is just the search for the knob settings that make the total loss small. Turn the knobs, watch the curve bend toward the points, stop when it fits well. Simple enough, but this is exactly where the trap is hiding. Watch what happens if we let the model get too powerful. Give it enough flexibility, and it can bend to pass through every single training point. Training loss, 0. But look at the shape. It's not capturing the pattern, it's chasing the noise. That's overfitting. The opposite failure is underfitting, too simple to capture the real trend, so it's wrong even on the training data. Somewhere in between is the model that captures the true signal and ignores the noise. And here's the catch. From the training data alone, the overfit model looks best. It has the lowest error. We need a way to tell the imposter apart from the real thing. What we actually want is called generalization, low error on new, unseen data drawn from the same source. That's the number that matters. The problem? We can't measure it directly. By definition, we don't have the future data yet. So we do the next best thing. We take some of our labeled data and hide it from the model during training. Then we use it to simulate new data. If the model does well on data it never trained on, that's real evidence it generalizes. This one move, holding data back, is the foundation of everything that follows. The purest version of that held-out data is the test set. You lock it in a vault at the very start and the model never touches it during training. At the very end, after all your choices are made, you unlock it once and measure performance. That number is your honest estimate of how the model will do in the real world. And there's exactly one rule, but it's sacred. You look at the test set once. The moment you start making decisions based on test performance, it stops being unseen data, it quietly becomes training data, and your estimate becomes a lie. But there's a gap. Along the way, you have to make choices. How flexible should the model be? Which settings? When to stop? To choose well, you need to compare options on unseen data. If you use the test set for that, you've broken the one rule. You're tuning to it. So we carve out a third pile, the validation set. You train on the training set, and you use the validation set to pick the model and settings that do best on it. Then, only at the very end, the test set gives the final verdict. Here's the analogy that makes it stick. The training set is your homework. The validation set is the practice exam you use to decide what to study, and the test set is the final, taken exactly once. Now we can see overfitting happen. As we let the model grow more complex or train it longer, plot two curves. Training error just keeps falling, of course. The model is fitting the data harder and harder. But validation error tells the real story. It drops at first as the model learns the genuine pattern. Then it turns and climbs as the model starts memorizing noise that isn't in the validation data. The gap between the two curves is overfitting. The sweet spot is the bottom of the validation curve, complex enough to capture the signal, not so complex it chases noise. That's the model you keep. One catch. If your dataset is small, a single validation set is just a few points, noisy, and you're wasting data by holding it out. The fix is cross-validation. Split the training data into, say, 5 folds. Train on 4, validate on the 5th, and rotate. Each fold gets a turn as the validation set. Average the 5 scores, and you get a far more stable estimate while every point gets used for both training and validating. The test set still stays in its vault, untouched. Cross-validation is just a smarter way to spend scarce data. Two things can quietly ruin all of this. First, the whole scheme assumes your train, validation, and test sets are drawn from the same distribution. The technical term is independent and identically distributed. If the real world you deploy in looks different from your data, a new kind of user, a shifted season, your honest test score stops being honest. Second, the human mistakes, leakage, where information about the label sneaks into the inputs, like accidentally including a column that's a stand-in for the answer, and peaking, where you tune against the test set until it's meaningless. Guard the split, guard the vault, and check that your data actually looks like the world you're predicting. So, the whole idea in one picture. Supervised learning fits a function from labeled examples, but the goal is generalization, doing well on data it has never seen. To pursue and measure that, we split our data 3 ways: the training set, to fit the model; the validation set, to choose the model and its settings; and the test set, locked away, to judge it once. Training error flatters you. Validation error keeps you honest while you choose. The test set tells the truth at the end. This isn't a trick for one algorithm. It sits underneath every supervised method, from linear regression to gradient boosting to deep neural networks. Get the split right, and everything else you build stands on solid ground. Thanks for watching. This is Gradient Canvas, where we make AI beautiful and understandable. If you enjoyed this and want to understand AI concepts, please like, subscribe, and share it with others. Join us to explore more AI concepts, from neural networks to transformers. See you in the next video.